Okay, so you've seen this formula, right? M equals N over V, probably 100 times. But what if I told you that more than half of university chemistry students get a super simple question about it totally wrong? Yeah, today we're going to dig into why molarity is so much more than just a formula and how you can actually master it.
All right, let's just jump right in with a challenge. This is a question that was given to first-year university chem students. And, it looks pretty straightforward, but don't let that fool you. Let's see if you can spot the trap here.
Okay, here's the deal. We've got three solutions. All of them have the exact same amount of solute. That's 0.20 moles. The only thing that's different is their molarity. One is 0.80 m, one is 1.0 m, and the last is 1.4 m. So the big question is, which one takes up the smallest amount of space? Which one has the smallest volume? Go ahead and pause if you need a sec to really think it through.
You ready for this? Get this. A whopping 50.5% of the students, yeah, more than half, picked the answer that was the complete opposite of the right one. That is a massive number. It tells you there's something about this concept that just doesn't click intuitively for a lot of people.
So, what in the world is going on? How can such a fundamental concept be so darn confusing? Well, to figure that out, we've got to go back to square one. Let's make sure we've got the basics totally locked down. You can think of every solution as a little story with three main characters. You've got the solute, the solvent, and then the solution they make together. So let's get properly introduced.
First up, the solute. This is just the stuff that gets dissolved. So if you're thinking about salt water, the solute is the salt. Simple enough.
And then you have the solvent. This is the thing that does the dissolving. Back to our saltwater example, this is the water. And when you mix them together, what do you get? The solution. It's that final, perfectly blended mixture. So just to recap, solute plus solvent equals your solution. Got it? Good. Okay, and that brings us right back to that famous formula. M equals N over V. Molarity is the number of moles divided by the volume. It looks so simple, right? But believe me, this is where the plot thickens. So what is molarity really? It's all about concentration. Think of it like this. How much stuff, or how many moles of that solute, have you crammed into 1 liter of the final solution? It's all about the ratio, the amount of stuff per a certain amount of space. And here we are. This is the single biggest trap when it comes to molarity. It's mixing up the amount of something with its concentration. I mean, they sound kind of similar, don't they? And the research is super clear. This is exactly where most people get tripped up. Let's really break this down. Moles, or N, that's just an amount. It's what we call an extensive property, which is a fancy way of saying it depends on how much stuff you have, right? If you have more solution, you have more moles. Simple. But molarity, M, that's different. It's a concentration. It's an intensive property. That means it doesn't care how much you have. It stays the same.
So what does that really mean? An intensive property doesn't change. Think about it like this. The saltiness of the ocean is the same whether you have a tiny little thimble of seawater or a giant bucket of it. The saltiness, the concentration, is constant. Now, obviously, the amount of salt is way different in the thimble versus the bucket, but the saltiness itself, the molarity, that doesn't change one bit. And look, this isn't just some small random mistake people make. Researchers have pointed this out specifically. A paper on this exact topic talks about the persistent failure of pupils to distinguish amount of substance from concentration. That's it. That's the heart of the confusion right there. Okay, so how do we sidestep this trap? The key is to stop thinking about it as just a formula you plug numbers into. Instead, we need to start thinking about the relationships between the variables. We got to think in proportions. Check out this last line right here. It says that when the number of moles, N, is constant, which, hey, is exactly the case in our original question, then molarity, M, and volume, V, have an inverse relationship. It's like a seesaw. If one goes up, the other has to go down to keep everything balanced. So let's use that logic to solve our riddle. Step 1, we know the moles are constant, right? 0.20 for all of them. Step 2, we just learned that means molarity and volume are inversely proportional. Step 3, applying that logic, if we want the smallest volume, we need to look for the highest molarity. And boom, there's our answer. The 1.4 m solution, the most concentrated one, has to have the smallest volume. See? It's all about the logic, not just punching numbers into a calculator. All right, so we cracked the case. But you might be thinking,
Okay, cool trick, but why does this matter so much? Well, it's because getting a real handle on molarity is absolutely essential for doing pretty much anything in chemistry. I mean, we're talking about everything from accurately preparing solutions in the lab to essential procedures like titrations, all the way to big picture stuff like stoichiometry and chemical equilibrium. Molarity is the bedrock. If you get that wrong, everything you build on top of it is just going to be on shaky ground. And that brings me to one last thought for you. Molarity is really all about amount of substance per unit of volume. It's a per unit rate. And if you think about it, these kinds of rates are everywhere. We use them all the time. Miles per hour, dollars per gallon, megabits per second. So here's my question for you. What other critical per unit rates define the world around you? Once you start looking for them, you'll realize they are absolutely everywhere.